Okay, Chapter 4, Section 3, L'Hopital's rule. In this section, we're going to revisit the same concepts that we studied back in Chapter 2 when we were working on limits, and we're going to add to it. Before we jump into how we're going to add to it, though, I want to take a few minutes to refresh our memories on what we did back in Chapter 2 so we can be ready for this new addition to those rules and to the ideas that we've already developed. Okay, so for example, let's say that this graph is given to us. For the moment, let's ignore the equation for the function and just deal with the graph. Finding limits by the picture, by the graph, is super easy. It really just gets complicated when we have to deal with the equations. So let's just think about this function here, right? So this whole thing in red is the function. It looks like the function is kind of defined by three pieces. So everything in red is the function. To the left of one, right, so f of x is kind of defined by this line here with some positive slope, right? Let's call this line A. Then there's this dot right there. I don't know what this height is here. I'm just going to make something up. How about if it's like at 1/2 right there? That's this guy right there. And then this looks like some sort of upside down parabola. So if I wanted to describe this graph, it would be something along these lines. It would be line A whenever the input values are strictly less than 1. So this would be 4 cases when x is strictly less than 1. For cases when x is strictly greater than 1, so for x is strictly greater than 1, we would kind of follow this parabola over here. And then for the specific case of when x equals to 1, then, well, it looks like it would be 1/2. Right? So this would be kind of like how we would describe it. Again, if we had specific equations, we might have an equation for this line. We might have an equation for this parabola. But for the moment, we're not going to worry about the actual equations. We're just going to kind of look at it and study the graph and learn from the graph. Okay, when we're dealing with limits, what we're interested in doing is figuring out a pattern of where the function is headed, where the outputs are heading as the inputs head toward a particular direction. So in this case, we might be interested in identifying the pattern that might happen to our function as x gets close to the number 1. So as we choose values of x in this direction, and maybe here and here and here and here, and they approach 1 from the right-hand side, and also maybe from this direction. So x is chosen there, and then there. As we choose values from either side, the output is going to get closer and closer and closer to something. So in this particular case, we see that from the left-hand side, the outputs are getting really, 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 really close to the number 2, right? Remember that in limits, we don't care about what happens at the actual number. We care about where is it going as we go there. So here we would maybe write something like this: the limit as x approaches to 1 from the left-hand side, from one direction, of our function f of x. From the picture, it looks like they're heading toward the number 2. This limit equals to 2. On the other hand, from the other direction, the limit as x approaches to 1 from the right-hand side, the limit as x approaches to 1 from the right-hand side of f of x, well, it looks like as I choose different values of x that get closer and closer to 1, they begin to get closer and closer. The outputs of our function get closer and closer and closer to 3. Okay? So the left-hand limit of this function as x approaches to 1 from the left-hand side is equal to 2. The limit as x approaches to 1 from the right-hand side of the function approaches to 3. These do not match. So in this particular case, we would say that the unrestricted limit, right, kind of because of both of those things, the limit as x approaches to 1, and then we don't put a direction. We say the unrestricted limit, it can approach 1 from either direction of our function, well, we would say it does not exist, right? Because there isn't a specific number it goes to. Sometimes it's heading toward 2, sometimes it's heading toward 3, depending on which side of 1 you select a value of x. So the unrestricted limit does not exist. If you at least, however, restrict yourself to only choosing values to the left of the 1, so you're approaching 1 from the left-hand side, then that limit does exist. It approaches to 2. And if you restrict yourself to choosing values of x that approach 1 from the right-hand side, then the limit does exist. And it's approaching to the number 3. Notice that, of course, the value of our function f of 1, in my little case, equals to 1/2, and this doesn't have anything to do with the limits, right? The limit cares about where it looks like it's heading without necessarily caring about that specific value at that point. So here's a nice little applet that conveys that same idea. This little black dot here is the output value as x approaches to positive 1 from the left-hand side. When x is way over here, when it's a negative value, the output begins way down here, and as x gets closer and closer to 1, the output values get closer and closer and closer to 2, as long as we're restricting ourselves to choosing x values that are to the left of 1. As we approach 1, as we get infinitely close to 1, but always from the left-hand side, the pattern is that the outputs are heading toward the number 2. On the other hand, as x approaches to 1 from the right-hand side, see, when x is like 4, there's an output value way down here, and as x gets closer and closer and closer to 1, but always from the right-hand side, the output values get closer and closer and closer and closer and closer to 3, right? So they're heading toward 3. So we'd say that the limit as x approaches to 1 from the left-hand side of this function equals to 2, proof by picture, and the limit as x approaches to 1 from the right-hand side is equal to 3, again, proof by picture. And notice that at the actual number 1, the output of that value is 1/2. It has nothing to do with the actual limits. Now, if we wanted to include the unrestricted limit, if we remove that little minus and that little plus there, if that's not there, that means that you're allowed to choose any value of x that's close to 1 from either side. And if we did that, we would notice that sometimes we're approaching 2 and sometimes we're approaching 3. Therefore, we're not approaching a specific number. So the limit as x approaches to 1 does not exist in this case. Okay, now let's take a look at another example. Let's say that we are given a function that looks like this, that's this red one, that almost looks like a parabola, except there's a little hole there. And at that value, and at that point, the output is 3, right? So it kind of falls out of line. There's a little hole there, and it kind of pops up to give you this little discontinuity. Okay. So we might be interested in what is happening to this function as the input values get closer and closer to 2. So we'd say that the limit as x approaches to 2 of our function, let's call the whole thing f of x. Now, the f of x is everything, including that, right? That little dot, everything in red is the function. So anyway, okay, so the limit as x approaches to 2 of f of x. I'm not going to restrict it by saying from the left side or from the right side, because I can see by my picture that both of them are going to match. No matter which value of x I choose, as long as I choose an x value, say from there, and then maybe choose a second value from there, and then another one, and another one, and another one, and another one, right? As the x values selected get really, really infinitely close to 2, I can see that my output values are going to travel and get closer and closer and closer and closer and closer and closer and closer to this value here, which I'm presuming is the number 1, right? This guy right there. Okay, so I can tell, proof by picture again, that the limit as x approaches to 2 of this function is going to be equal to the number 1, right? And again, note that the actual value of my function at 2 is equal to 3. And that's okay. The limit exists. The limit cares about the pattern of where the values, the output values, are heading, right? What it looks like. It looks like it's heading that way, right? If all we had was these black dots, right? All these black dots here, that's all we had, and you were asked to guess what's going to happen at that point, well, I think most reasonable people, the most reasonable guess would be that it's going to be right there, that it's going to be an output of 1 would be a good guess based on all these other black dots that are heading there. The fact that at that actual point, the real answer is way up here has nothing to do with the pattern that we've established, right? So the limits care about what it looks like, not what it actually is. And it looks like it's heading toward 1. Okay, so that same applet helps us visualize that. These 2 little black dots represent the outputs as we choose values of x that get infinitely close to 2 from either side. So either a little bit less than 2 or a little bit more than 2. As we approach 2 from either direction, they're both squeezing into this value. They're getting infinitely close to 1. So the limit as x approaches to 2, unrestricted, of f of x equals to 1. Right? And again, it doesn't matter that the actual value at 2 is a 3. Okay, here's another example we might run into, something that looks like this. This function has a vertical asymptote at 2. Right, so let me put it in green. So this function has a vertical asymptote at x equals to 2. At x equals to 2. So as we let x values be selected that get infinitely close to the number 2 from either direction, unrestricted, we see that the output values are just going to climb higher and higher and higher and higher and higher. The closer you get to 2, the higher this climbs, right? It grows toward infinity. This direction grows toward infinity. It gets infinitely large. No matter how big of a number you choose, I can always think of a number that's so close to 2, so infinitely close to 2, that its output value will be bigger than any number you can think of. Right? That's what that means, that it's going toward infinity. So we write that down by saying that the limit as x approaches to 2 of my function f of x, remember everything in red is my function, is equal to positive infinity. Now this means that it doesn't exist because it's not heading to a specific number. This is same as a does not exist answer, except that it just gives you a little bit more information. It tells you how it doesn't exist. It doesn't exist in the form that it goes toward positive infinity. In the example that we did earlier, where we had the unrestricted limit, and in one direction it headed toward 2, in the other direction it headed toward 3, in that case it didn't exist for a different reason, right? The left limit didn't match the right limit. We can also do the same thing for restricted limits. So the limit as x approaches to 2 from the right-hand side of f of x. Well, in this case, it's going to match the same thing as the limit as x approaches to 2 from the left-hand side of f of x, which is going to be the same thing as our unrestricted limit. No matter what, we're still going to head toward positive infinity, and it doesn't exist. Okay, so here our little applet is demonstrating how that happens. Right, so those little black dots are indicating the output values. As we choose x values, get closer and closer and closer to that number 2, and it doesn't show it on here, but there's a little 2 here. So as the input values get closer and closer to the number 2 from either side, the output values get larger and larger and larger and larger and larger, and they just shoot off toward positive infinity. We can also have a case like this, where the left limit and the right limit don't match. So as x approaches to the number 2, from the left-hand side, the output values are heading toward negative infinity. And the limit, as x approaches to 2, from the right-hand side, the limit is approaching positive infinity. Both of them, again, both of them really mean that the limit doesn't exist, but you can include that it equals to positive or negative infinity as a way of providing more information. But if the question was, does the limit exist as x approaches to 2 from either side, the answer is no, the limit does not exist. Okay, now let's take a look at this function. Remember that so far we've only been looking at cases with x approach some specific constant, and we could have a case where as x approached that constant, maybe the limit does exist, maybe only one side limits exist, but not the unrestricted limit. It could be that the limit goes off to positive or negative infinity. And then the other thing we studied back in chapter 2 is cases where we're looking to see what happens to the function as x goes out to positive or negative infinity. So this time we're considering the outputs of our function as x grows toward positive infinity, or the outputs of our functions as x goes toward negative infinity. So we can see from this graph that as we approach, as the input values, as x approaches negative infinity, the output values seem to be getting closer and closer and closer and closer to 0, right? So that's the limit as x approaches negative infinity of this function would be 0. On the other hand, in this direction, it looks like the limit as x approaches positive infinity, looks like the output values seem to be getting infinitely close to the number 2. Okay, so remember the function itself is everything in red, including this dot, right? This little dot right there indicates that when we want to evaluate our function at 0, the output is negative 2. So from this picture, this seems to be shooting off toward infinity. So I would write down that the limit as x approaches to 0 of my function side, right? So it's a does not exist, does not exist. And again, note that the actual value of my function at 0 seems to be negative 2. Okay, so this is the cases where we're letting x approach a specific constant, the limit as x approaches a constant from either side. So we were selecting values of x that danced around that number. It's unrestricted, so either side. So as x approaches to 0, right, as x got closer that way and x got closer that way, I choose values, values, values. I would see that my outputs are just heading toward positive infinity. Good. Okay, on the other hand, we could analyze the cases where we're letting x go toward positive infinity. So the limit as x approaches to positive infinity as the input values of my function, as we're choosing values of x there, and they keep going that way. Another x there, another x there, another x there. We keep choosing x values that way until we go toward infinity. Is there a pattern for the output? And this graph seems to be indicating that as we choose input values that get infinitely large, the output values seem to get infinitely close to 2. Right? This is converging toward 2. So the limit as x approaches to infinity of my function f of x is equal to 2. On the other hand, in the other direction, as I choose x values that get closer and closer to negative infinity, maybe an x value there, an x value there, an x value there, right? We go that way until we go toward negative infinity. It looks like my output values are getting closer and closer and closer and closer to the x-axis, which means they're getting closer and closer to 0. So we would write down that the limit as x approaches to negative infinity of f of x is equal to 0. Okay, so notice the distinction. Sometimes we have that the limit as x approaches some constant, and the thing we write down as the answer could be the infinity symbol, which means it doesn't exist. And then this, we might be in another thing we might consider is the cases where x is itself heading toward infinity, and we want to know where is the function headed, if it's heading to a specific value. right? Now, it's possible it doesn't head toward any specific value. Maybe it just shoots off toward infinity as well. So it doesn't necessarily have to exist. Okay, well, all of these were based on graphs. Let's take a look at a couple of other common graphs. Okay, so far we've only been looking at cases where a picture is given to you, a graph, not necessarily connected to any actual equation, and we're asked to find the limit based on the picture, so sort of proof by picture, and I hope that that's pretty easy to do. I think finding limits from a graph is very easy if you know what you're looking for. However, things get a lot more complicated when we have to deal with an equation instead of just a given picture or a given graph. So here's a couple of classic situations, basic equations, in the some notation. So we have equations, we have graphs, and then the types of limit questions we might be asked. So for example, we might have just a straightforward straight line like this one. This is the equation y equals to x. And we might be asked to consider the limit as x approaches to 0 of this function x. So when we, again, in this case, maybe we graph it and study it. So if we are choosing x values that get infinitely close to 0 from either direction, we see that the graph is also approaching 0. That's why this is true. The limit as x approaches to 0, unrestricted, right? So it's from either side, of the function x equals to 0. On the other hand, what if we consider the case where x is heading out toward positive infinity? As the x grows toward positive infinity, we see that our output values are also going to grow toward positive infinity. So that's where we get this. The limit as x approaches to infinity of the function x equals to positive infinity. And likewise, as x grows toward negative infinity, as we choose values of x that go in this direction and head that way toward negative infinity, we see that the output values are also growing down toward negative infinity. Good. So that's where this is coming from. Okay, let's look at a standard parabola, y equals to x squared. We could also ask the same thing, the limit as x approaches to 0 on x squared. So as x is chosen to approach 0 from either direction, we see that the function output values are going to head toward 0 as well. If we had a different value, right, 0 is just kind of an arbitrary choice your author made to just kind of give you some examples, but it could be something else. How about the limit as x approaches to the number 2 on the function x squared, right? So the number 2, let me erase some of this over here. 1, 2, here's the number 2, and then it's heading this way, so we know it's going to be there at 4. So as x is chosen, as we let x approach 2 from either side, we get infinitely close to 2 on either side. We know that the output values are going to approach the number 4. Right? So they go that way, and they go that way, and they get infinitely close to 4. So the limit as x approaches to 2 on the function x squared equals to 4. Okay. What about these, right? So the limit as x goes toward positive infinity, as the x values are chosen to be larger and larger and larger, right? As they head that way toward positive infinity, we can see that these values are going to go toward positive infinity. And as x values are chosen to go this way toward negative infinity, larger and larger and larger toward the negative direction, we can see that the output values are also heading toward positive infinity. That's what this statement is. Good. All right, there's another classic example, y equals to 1 over x. And we can see that as x approaches to 0 from the right-hand side, as the values of x get closer and closer and closer and closer to 0, never actually 0, but get infinitely close to 0, we see that the output values are heading toward positive infinity. So that's where this statement comes in. The limit as x approaches 0 from the right-hand side of our function 1 over x, that equals to infinity. The limit as x approaches to 0 from the left-hand side, so now as we approach 0 but always remain to the left of it, get closer and closer and closer and closer, but always to the left of it, we see that our output values are heading toward negative infinity. That's what that means. The limit, so the unrestricted limit, right now, if we just say get close to 0 from either side, sometimes it's going to be a large positive number, sometimes it's a large negative number. So we can't really say positive or negative infinity. We could just say it just doesn't exist, right? Again, to be clear, these two are also cases of does not exist, but at least we can give some information of how it doesn't exist. In this case, in the unrestricted limit, we can't even do that. Okay, and now the other kind of question, what if x is growing toward positive infinity? Very large numbers, infinitely large numbers, as I input infinitely large numbers, we can see that this is going to start heading towards 0. The output values head towards 0 as the input values head toward positive infinity. That's what this means. Good. And in the other direction, the same thing happens. As x grows toward negative infinity, in this direction, the output values grow toward 0. Right? And that's how we get that. Finally, we saw an example like this just a few minutes ago, but now we have an equation tied to it. This kind of graph is equal to 1 over x squared. And so we see that the limit as x approaches to 0 from the right-hand side of our function approaches to positive infinity. Right? It's infinitely large. Same thing happens from the other direction. The limit as x approaches to 0 from the left-hand side, so always approaching from the left-hand side, we see that the output values are still growing toward infinity. So the unrestricted limit as x approaches to 0 from either side is going to be infinity. And remember that all of these three cases still mean that it does not exist. Good. Okay, and then the limit as x approaches that way toward infinity, we see that the output values are heading toward 0. And as x approaches to negative infinity, we see that the output values are also heading towards 0. Okay, so again, hopefully proof by picture is pretty easy. We can identify where things are going by looking at the picture. Some of the most basic equations, we can easily graph it or at least sketch it and have some sense of where the function is going. But as you recall in Chapter 2, we very often are given very complicated equations, and we could use technology to graph the really complicated equations and then be able to tell what the result of the limit would be based on the graph. However, we don't always have the luxury of doing that, and proof by picture isn't really a proof at all. So we have to work with the equations. Right? We have to be able to look at an equation, work with it, manipulate it, use all the rules from Chapter 2 to be able to solve limits. Okay, so that's what we're doing in this section. We're going to come back and solve limits, but we are going to add to those rules. For example, again, back in Chapter 2, we might have been asked to find something like this. What is the limit? The limit as x approaches to 1 of x squared plus 4x plus 5 divided by x minus 1. Minus 5. Okay, so notice that if we just simply plug in a 1 into this, we get a 1 plus 4 minus 5. So that would be 1 plus 4 is 5 minus 1. We end up with a 0 in the numerator and then a 0 in the denominator. So it doesn't quite make sense in that case to just plug in a 1. So one of the tricks we learned in Chapter 2 is that what we could do is say that this is equivalent to the limit as x approaches to 1. And what we could do is factor the numerator. This is x plus 5, x minus 1. And then the denominator is x minus 1. And so back in Chapter 2, we learned that we could go ahead and cancel those. And that this limit is equal to the limit as x approaches to 1 on just x plus 5. And now we can just plug that 1 in there. So this becomes 1 plus 5, or 6, right? And this 1 right here comes from the fact that it's there. Okay, so this is just the work we would do in Chapter 2. Fun with Chapter 2 stuff. Okay, another thing that we did back in Chapter 2 would be maybe to work with something that looks like this. Say, find the limit as x approaches to infinity of, say, 2x cubed plus 2x squared minus 7 divided by x cubed plus 4. And again, back in Chapter 2, one of the tricks we learned when we're working with a limit as x approaches to infinity, is to multiply the numerator and denominator by 1 over x to the power of the largest degree found in the denominator. So if we multiplied everything in the denominator by 1 over x cubed, multiply everything in the numerator by 1 over x cubed, we'd get the following. We'd end up with 2 over 2x cubed divided by x cubed plus 2x squared divided by x cubed minus 7 divided by x cubed all over x cubed plus 4 over x cubed. Okay, now a bunch of stuff reduces. This reduces with that completely. This reduces with that, and then that doesn't reduce. These guys cancel, and so we end up with this equaling the limit as x approaches to infinity of just 2 plus 2 over x minus 7 over x cubed divided by 1 plus 4 over x cubed. And then we know that, well, there's several properties of limits. We know that we can separate this into pieces. We can find the limit of numerator and denominator. Okay, so we can follow all those rules from Chapter 2, and ultimately we know that this is going to equal to 0, this is going to equal to 0, this is going to be equal to 0, and so we'll get that the limit equals to 2. This limit equals to 2. Okay, I know I'm going really quickly through it, but I'm just refreshing your memory on some of the stuff we did in Chapter 2. If you don't remember some of this, then go back and watch those videos from Chapter 2. Okay, so if we graph these equations, we can confirm that our limit is valid. So in this case, let's graph it and show that the graph confirms that as x approaches to 1, the limit as x approaches to 1 equals to 6. Okay, so here I graph that really complicated equation, x squared plus 4x minus 5 all over x minus 1. And its graph turns out to look like this, almost a straight line. Now, Desmos is actually lying to us because it's not a solid line. There's actually going to be a little hole here at x equals to 1, right? Because 1 is not in the domain of this. But Desmos, that's one thing I don't know how to get it to do, to identify all those little holes. So there's really going to be like a little hole there. At any rate, though, whether there's a hole or not, the limit doesn't care about that. We care about what happens as x approaches to 1, not what actually happens at 1. And we can see that as x approaches to 1, as the input values approach 1, the output values approach 6. Let's see if I can, there we go, that's better. As x approaches to 1, then the output values are approaching 6, right? So it confirms what we got from our equations. On the other hand, okay, so here's that other equation. If I come to Desmos and I graph it, I can see from our picture it confirms that as x gets infinitely large, as x approaches to positive infinity, the output values here are approaching the number 2. Zoom in a little bit more. See, here's the number 2. As the input values get larger and larger, as x is chosen to be a value that's larger and larger and larger and larger, the output values get infinitely close to the number 2. Right? So there's a horizontal asymptote at y equals to 2. So that confirms our work. Okay, so hopefully this has been a nice little review of all the great work we did back in Chapter 2 with regards to limits. So sometimes we have a graph and no equation, and we can just identify a pattern of where the function is heading just based on the picture. Hopefully that's pretty easy. But very often we have to work with an equation. And even though we have technology and we can just easily go to like Desmos or another online graphing tool to graph it and be able to judge the limit based on the picture, that's not always going to be valid. We need to work with the equations. So we needed to learn rules on how to find those limits based on working with equations. So here's a couple of great examples of how to work with the equations. Sometimes we get to factor the numerator, cancel, reduce, and get to something, find our limit that way. Sometimes we get to use this kind of trick to rearrange our equations and be able to find the limit. And there's a variety of other rules and ideas that help us find limits based on an equation, all of them jam-packed into Chapter 2. But even all those rules are not going to help us find the answer to everything. There's going to be equations where none of the rules we've learned up to now will help us find that limit. For example, what if we were asked to find this limit? The limit as x approaches to 2 on the function e to the x minus e to the second power on x minus 2. Okay, notice that if we just plug in a 2, we'll get a 0 in the denominator. And we plug in a 2 here, we'll get e to the second power minus e to the second power. Well, we'll get like a 0 over a 0. So that's not really an answer. And we really can't do either one of these tricks. We really can't simplify the whole thing by multiplying the numerator and denominator by a clever division like this case. That's not going to work for us. And also, we really can't factor this into something that reduces and cancels and gives us our answer. So if this question was given to you back in Chapter 2, we'd be stuck. Luckily, this is where we use this new idea that I'm about to introduce called L'Hopital's rule. So this is what L'Hopital's rule states. Okay, L'Hopital's rule. Suppose that f and g are differentiable and that g prime of x does not equal to 0 on any open interval I that contains a, except possibly at a. Remember, the limit only cares about what's happening as we approach the value a, not at the actual value of a. Okay, so if the limit as x approaches to a of f of x equals to 0, and the limit as x approaches to a of g of x equals to 0, or, and these are kind of two separate situations here, or the limit as x approaches to a of f of x equals to positive or negative infinity, and the limit as x approaches to a of g of x equals to positive or negative infinity. In other words, we have an indeterminate form of the type 0 over 0 or infinity over infinity. Then the limit as x approaches to a of f of x divided by g of x is going to be equal to the limit as x approaches to a of f prime of x divided by g prime of x, if the limit on the right-hand side exists, or is positive or negative infinity. Okay, what is all this saying? Okay, so if we are facing a situation where we are asked to find the limit as x approaches to a of some function f of x over g of x, right? Some function there, and they're asked us to find the limit of the whole thing. What's happening there? What we're going to do is kind of go do a little bit of side work here and kind of note that if I find the limit as x approaches to a of f of x, and if I find the limit as x approaches to a of g of x, let's say that both of these happen to be equal to 0. This is what we call an indeterminate form of the indeterminate form of the type 0 over 0, right? Because the limit of the numerator is 0, the limit of the denominator is 0. And this is where L'Hopital's rule can come in. What L'Hopital's rule is saying is that in order to find that limit that we're interested in, limit as x approaches to a of this ratio function, f of x over g of x, what we could do is instead find the limit as x approaches to a of this new fraction, which is going to be the derivative with respect to x of the f of x function, divided by the derivative with respect to x of the g of x function. This new ratio over here will have a limit that is equivalent to the original one if it exists, or if it equals to positive or negative infinity. Okay. Let's, for example, revisit the question I just had a minute ago. So I'm going to erase all of this. So, for example, just a minute ago, I wrote down this question. Find the limit as x approaches to 2 on the equation e to the x minus e squared all over x minus 2, right? Find that limit. Well, that's ugly. I'm not really sure. But note that, so I put kind of like note that the limit as x approaches to 2 of just the numerator, e to the x minus e to the second power. Well, this is just some constant. Remember, e is just a number. E squared is just some number. So it's the same thing as just putting like 4 or 7, right? It's just some number. And e squared, e to the power of x, well, that's continuous. So because it's continuous, I can just replace the value of x with the 2. This is equal to e to the power of 2 minus e to the power of 2, where this 2 is the result of that guy right there. And, well, e to the second power minus e to the second power, that's just going to be 0. Okay. Now, in the denominator, the limit as x approaches to 2 of the function x minus 2, well, again, this is a linear equation. It's continuous. So from our rules in chapter 2, we know that we can just replace the x and say that this is 2 minus 2. Again, this 2 is the one from there, replacing the x with that 2, which again just gives me a 0. So this satisfies this condition. The limit of just the numerator is 0. The limit of just the denominator is 0. This is an indeterminate form of type 0 over 0. This whole question here is an indeterminate of the type 0 over 0. Okay? All right, well, according to L'Hopital's rule then, in order to find my answer, what I could do is just take the derivative of the numerator, take the derivative of the denominator. Hopefully, maybe, that will give us the limit we're interested in. So this is what we would do. We'll take the limit as x approaches to 2 of e to the x minus e to the second divided by x minus 2 is equal to the limit as x approaches to 2 of the derivative with respect to x of e to the x minus e to the second divided by the derivative with respect to x of the denominator, which is x minus 2. The derivative of the numerator by itself, well, that's just some constant, that's 0. And the derivative of e to the x, well, we know that that's just going to be e to the x. And the derivative of the denominator, well, that's a 0. And the derivative of x is just equal to 1. That's just going to be equal to 1. So we get that this is going to be the limit as x approaches to 2 of the function e to the x over 1, which is just going to be e to the x. And so this is just going to be equal to e to the second. Okay? Some constant. Remember, the number e is just a number. It's 2.718-ish. And so that's our answer. It approaches e squared. Okay. In some cases, we'll run into situations where we have an indeterminate of the form 0 over 0. Or in some cases, we'll run into a situation where we'll have an indeterminate of the type infinity over infinity. So you might have a case where you independently check out the limit of the numerator, the limit of the denominator, and maybe they both equal to positive or negative infinities. So you'll have a situation like this one. In either case, the L'Hopital's rule applies. Okay, so we'll do more examples, but let's note a couple of things here. So L'Hopital's rule says that the limit of a quotient of functions is equal to the limit of the quotient of the derivatives, provided that the given conditions are satisfied. Oh, and also one more thing I forgot to note here. It's customary to kind of let the observer, say in this case me when I'm grading your test or something, to recognize why this is allowed. So it's pretty common to put like say something like an LH kind of thing, like right over the equal sign. That way we know that this is where you employed L'Hopital's rule, and that this limit is equal to whatever result we get over here, this limit, by L'Hopital's rule. Okay, so note number one, L'Hopital's rule says that the limit of a quotient of functions is equal to the limit of the quotient of the derivatives, provided that the given conditions are satisfied. So it is especially important to verify the conditions regarding the limits of f and g before using L'Hopital's rule. Okay, and note number two, L'Hopital's rule is also valid for one-sided limits or for limits at infinity, both negative infinity or positive infinity. That is, we can replace the x approaches to a, can be replaced with the symbols x approaches to a from the right-hand side, x approaches to a from the left-hand side, x approaches infinity, or x approaches to negative infinity. Right? So in other words, coming back up here to the statement of L'Hopital's rule, these guys right here, instead of x approaches to a, could all be replaced by any one of these symbols. The limit as x approaches to a from the right-hand side, the limit as x approaches to a from the left-hand side, the limit as x approaches infinity, or the limit as x approaches to negative infinity. All right, let's do a few more examples. Okay, let's say we're asked to find this limit, the limit as x approaches -1 of this ratio, x plus 1 in the numerator, and x squared minus 7x minus 8 in the denominator. Let's first of all check the conditions for L'Hopital's rule. So if we try and evaluate the numerator, the limit as x approaches to -1 of x plus 1, we know that this is a polynomial. So this is a polynomial. And we know from chapter 2 that if we're trying to evaluate a polynomial, all we have to do is, if we're trying to evaluate the limit of a polynomial, all we have to do is evaluate the polynomial. So this is going to be equal to having blank plus 1, and all we have to do is evaluate the -1 there. So we see that this is just going to be 0. Okay. Likewise, if we think about the limit as x approaches -1 of just the denominator, x squared minus 7x minus 8, again, this is just a polynomial, some polynomial. And we know that the limit of a polynomial is equal to that polynomial evaluated at our limit value. So this is going to be equivalent to something squared minus 7 times something minus 8. And so this is going to be minus 1 there. And we see that this whole thing is going to be equal to 1 plus 7 minus 8, which equals to 0. So we see that this is going to be an indeterminate form of the form, right, this limit. This limit is indeterminate. Form of type 0 divided by 0, right? The limit of the numerator is a 0. The limit of the denominator is a 0. So we're going to attempt to solve this by L'Hopital's rule. So L'Hopital's rule says that the limit that we're after, this limit, is equivalent to the limit of taking the derivative of the numerator and taking the derivative of the denominator, right? So let me rewrite that. The limit as x approaches to -1 of this function, x plus 1, x squared minus 7x minus 8, the limit as x approaches to -1 of this by L'Hopital's rule LH it, L'Hopital's rule, says that this is going to be equivalent to the limit as x approaches to -1 of, and now we're going to take the derivative with respect to x of the numerator, and then separately the derivative with respect to x of the denominator, x squared minus 7x minus 8. Notice that this is not the quotient rule. We're not doing low d high minus high d low over denominator squared we go. We're not doing that. This is just simply straightforward, the derivative of the numerator separate from the derivative of the denominator. So let's go ahead and take that derivative. This is going to be the limit as x approaches to -1 of, and then in the numerator, this becomes 1. Right? The derivative of the numerator on its own is just the 1, and the derivative of the denominator ends up being 2x minus 7. 2x minus 7. Okay, so now this is a rational function, right? The whole thing, it's a rational function. And we know from our work from chapter 2 that this is equivalent to just evaluating it at the value of our limit, that -1, as long as we don't have a 0 in the denominator, which we are not going to have here. So let's just evaluate. This is equal to 1 divided by 2 times blank minus 7. And that blank is going to be that -1, which means that this is going to be equal to -1 over 9. Right? -2 minus 7 becomes -9, so the whole thing is -1/9. Okay, so this is the limit we were interested in. On initial inspection, we see that this has a limit of 0 in the numerator. The limit of this of the denominator is a 0, so we have an indeterminate form of type 0 over 0. And so L'Hopital tells us that in order to find this limit, it's equivalent to the limit of taking the derivative of a ratio of the derivatives, a ratio of the derivative of the numerator and derivative of the denominator. Not the quotient rule, just kind of taking derivatives separately, if it exists. So then we work our way, we solve, simplify, and end up with this. So then our connection is that the limit we were originally interested in, the limit as x approaches to -1 of x plus 1 over x squared minus 7x minus 8, that original derivative we were interested in, is equal to -1/9. So note that this particular limit had an alternative way of solving it if we used chapter 5 techniques. Let me zoom into this little corner over here. We had an alternative way of solving this particular question. So note that if we have the limit as x approaches to -1 of x plus 1 over x squared minus 7x minus 8, another thing we could have done is said that this is equivalent to the limit as x approaches to -1 of, and then factor the denominator. We would have gotten an x plus 1 times an x minus 8, multiplying this, so that's x squared minus 8x plus 1x gives me that minus 7x minus 8, so we get this. And now we can reduce these, and what we have left over is the limit as x, this is the limit as x approaches to -1 of 1 over x minus 8. Again, a rational function. We know we can just evaluate this to get our answer, get our limit. And so this becomes 1 over, and then we plug in that -1 minus 8. Minus 8 give me -1 over 9. So we would have gotten the same answer, right? That's the point. We can have the same answer in multiple ways. The point here is that we were able to use L'Hopital's rule to get the same answer we would have gotten by the techniques we developed back in chapter 2. I'll say by chapter 2 methods. But this helps us confirm that L'Hopital's rule is working. It's giving us the right answer. We won't always be able to do this, right? So this only works out well because we're able to factor the denominator and because it reduced with this term in the numerator. And that was just like a really happy coincidence. But L'Hopital's rule is a lot more powerful. It'll let us solve lots of other problems that we wouldn't otherwise be able to solve. So it's a very, very important tool that we get to use. Okay, so let's move on to other examples. Okay, let's say that we are asked to evaluate this limit. The limit as x goes to positive infinity of this ratio. First of all, let's explore this using our techniques and methods from Chapter 2. So if this was a question back all the way back when we were in Chapter 2, maybe one of the things we try is the following. Let's say that this is equivalent to the limit as x approaches to infinity of, and then we have 5 minus 4x to the third power and 1 plus 7x to the third power. So maybe we'd multiply the numerator and denominator by 1 over x to the third power, 1 over x to the third power. So the idea is to multiply by 1 over x to the power of the largest degree we see in the denominator, which then equals to the limit as x approaches to infinity of 5 over x cubed minus 4 all over 1 over x cubed plus 7. Good. Okay, and now we have this giant limit like this. Then this is going to be equal to the limit. We can break this up into little pieces here. This is the limit as x approaches to infinity of 5 over x to the third minus the limit as x approaches to infinity of the number 4 divided by the limit as x approaches to infinity of 1 over x to the third power plus the limit as x approaches to infinity of the number 7. And again, using our rules from Chapter 2, we know that this is going to go towards 0. This is going to go towards 0. This is just going to go toward 4, and this is going to go towards 7. So we end up with 0 minus 4 divided by 0 plus 7, or just negative 4/7 as our limit. Okay, but this is by the methods of Chapter 2. By chapter number 2 methods. Now let's try doing it by a newly discovered L'Hopital's rule and confirm that we get the same answer. So let me start all over. So let's say again that I have that I'm interested in this limit, the limit as x approaches to infinity of 5 minus 4x to the third power over 1 plus 7 x to the third power. So rather than finding the limit of the numerator separate from finding the limit of the denominator, very often, sort of in writing, what happens is that people just proceed forward to see if it's going to work out or not. So let's find the limit of the numerator. That's 5 minus 4x to the third power. And then the limit of the denominator is the limit as x approaches to infinity of 1 plus 7x to the third power. And then think about what happens here. The limit as x goes to infinity, well, this part doesn't even have an x, so it's just 5. That doesn't matter. And as x gets infinitely large in the positive direction, x goes toward positive infinity. And then there's this minus 4, so it goes toward negative infinity. So the numerator is heading toward negative infinity. In the denominator, numbers, the inputs are getting infinitely large in the positive direction and then getting cubed. Well, that just makes it an even larger positive number. Times 7 makes it an even larger positive number, plus 1 makes it an even larger positive number. This denominator is heading toward positive infinity. So this is an indeterminate of the form. Right, so this limit is an indeterminate form. Of type infinity over infinity. Right, that's what's happening here. So by L'Hopital's rule, then we can say that this limit, the limit we are interested in, the limit as x approaches to infinity of this fraction, 5 minus 4x to the third power, 1 plus 7x cubed, is equal to the limit as x approaches to infinity of of the derivative with respect to x of the numerator, 5 minus 4x cubed, divided by the derivative with respect to x of 1 plus 7x cubed. Right? The derivative of the original ratio I'm interested is equal to the derivative, the limit of the original ratio I was interested in is equal to the limit of the ratio of these two derivatives. Right? And that's where L'Hopital's rule is coming in. Right? Make sure you identify when you're using L'Hopital's rule. Right? That allows that to happen. On the test, when you show your work, please identify with something like this or some sort of indication of when you're allowed to do this, when you're implementing L'Hopital's rule. Okay, so now this then becomes equivalent to the limit as x approaches to infinity of this ratio, which is going to be 0 minus 12, so minus 12x squared. And in the denominator, we'll have 21 x squared. Now these x's cancel. And we're left with just the limit as x goes to infinity of just negative 12 divided by 21, just a constant. So the answer is just that constant, negative 12 divided by 21, which can be reduced as 4/7. So 3 goes into 12 4 times, 3 goes into 21 7 times. So we have our answer is negative 4/7. So we can wrap it all up and kind of put a bow on it and go back to our original statement, the limit as x approaches to infinity of the original ratio we were interested in, 5 minus 4x cubed, divided by 1 plus 7x cubed is equal to negative 4/7. And this answer matches what we would have gotten had we used the techniques from chapter 2. Right, same. So you don't have to solve the answer in 2 different methods in your homework, by the way. I was just simply pointing out that the methods that we learned back in chapter 2 happened to work for this problem, and we got an answer of negative 4/7, and I just wanted to compare and contrast and show how L'Hopital's rule works, and it gives us the same answer. But in this section and in this next exam, I'm expecting people to do things by L'Hopital's methods. So that's what we should be doing in our homework. And let's do some other examples where the methods from chapter 2 might work, might not work, but let's get comfortable with L'Hopital's rule. I think eventually people realize that it's a really nice, really powerful tool and often helps us solve the answer in a nice, easy way. Okay, so let's say we're asked to find this limit, the limit as x approaches to 0 of ln of 1 minus 3x all over x. Yeah, the ideas from chapter 2 don't really work out here. So let's just jump right into L'Hopital. So we would begin by confirming that we're allowed to use L'Hopital. So I would begin this problem by thinking about the limit as x approaches to 0 of the function in the numerator, ln of 1 minus 3x. and then the limit as x approaches to 0 of the function in the denominator, kind of thinking of this. Okay, in the denominator, this limit is going to go toward 0. In the numerator, we have a function, and then we have another function inside it. This is a composition of functions. Back using our properties from chapter 2, we know that we can pull this inside that function and find this limit, and then evaluate the outside function at that limit, as long as the inside function has a limit that exists, and the outside function is continuous at that point. Right? So this is equivalent to ln of the limit as x goes to 0 of 1 minus 3x, like that. So we just kind of think about the limit inside the argument of the ln function. And it's going to be okay as long as this limit exists and that the ln function is continuous at that limit. Okay, so let me rewrite this over here. And you know what? I'm just going to extend this here and say that this is the limit as x approaches to 0 of x. And we'll extend this guy over here, just that it's on the same line. Okay, so the denominator, we said this limit is 0. Now in here, inside this argument, let me highlight that it's inside of it, right? So this whole limit, the limit of 1 minus 3x, is inside the ln function. And this limit inside here is going to go toward 1, right? As x goes infinitely close to 0, this is a polynomial, so we can just evaluate it at 0. So this is going to head toward 1. And then the ln function is continuous at 1. And so the whole thing is going to go toward ln of 1. This whole thing goes toward ln of 1. And ln of 1 is 0. So this is an indeterminate form of the type 0 over 0. Okay, so it's an indeterminate form of the type 0 over 0, which now means we can use L'Hopital's rule. Okay, so now let's copy this down here, which means that ln, the limit, as x approaches to 0 of ln of 1 minus 3x over x. Right, so we have this limit of this ratio, that this is equivalent to the limit as x approaches to 0 of, and now we're going to take the derivative with respect to x of ln of 1 minus 3x divided by the derivative with respect to x of just x. Okay, so now this derivative is nice and easy, and this derivative is nice and easy. This one is just going to be 1. And this derivative is maybe a little bit more complicated. This derivative is going to be 1 over the argument of the ln function. So it's going to be 1 over 1 minus 3x times the derivative of the inside part, thanks to our chain rule, 1 minus 3x. And then that turns out to be an extra negative 3. Negative 3. So our entire derivative is then going to be equal to negative 3 all over 1 minus 3x. And that's what that is. So this means that this is the limit as x approaches to 0 of this new ratio, which just has a 1 in the denominator and a negative 3 over 1 minus 3x in the numerator. Okay, well then this just simplifies to give me the limit as x approaches to 0 of negative 3 over 1 minus 3x. This is a rational function, and we know that rational functions can just be evaluated at the index of the limit as long as that limit exists and it isn't 0 in the denominator, which it won't be in this case. So this is just going to be equal to negative 3 divided by 1 minus 3 times, and this is where we just get to put in a 0 in there, and then this just becomes negative 3. Okay, So we bring it all together and say that the original limit we were interested in, the limit as x approaches to 0 of ln of 1 minus 3x divided by x is equal to negative 3. Ooh, I forgot to identify when I used L'Hopital's rule, so LH, right there. That's when I used it. The limit of my original ratio is equal to the limit of the ratio of the derivative of the numerator divided by the derivative of the denominator. Okay, so don't forget that we have to confirm that we have a limit that qualifies for L'Hopital's rule. We have to check the limit of the numerator, the limit of the denominator, and we must have something that is either of the type 0 over 0 or infinity over infinity, plus or minus. If we have an indeterminate of one of those two forms, then we can apply L'Hopital's rule. Don't forget to be very careful with the notation. In order to get full credit on this next test, you don't want to miss out on points by doing weird notational things. Even if you have the right idea, I can only grade what's in front of me and what you've written down, so don't accidentally write things down that aren't true. So be careful with the notation. The limit, the original limit of the ratio we were interested in, is equal to the limit of, and then it's the derivative of the numerator divided by the limit of the denominator. Right? Then you can simplify, reduce, you can use our methods from chapter 2 at that point, and hopefully you get to a nice answer at that point. Okay, let's try a couple more. Okay, let's say we're tasked with finding this limit. Okay, let's begin by evaluating the limit of the numerator, limit of the denominator. This is going to be equal to the limit as x approaches to infinity of e to the 3x divided by the limit as x approaches to infinity of x to the third power. And if we think about the graph of e to the power of 3x, we see that as x goes toward infinity, this is going to grow toward infinity, right? To note that if we have some function y equals to e to the x power, its graph will look like this. Its graph will have this sort of a shape, like that, as long as x is going toward positive infinity. So as x goes toward positive infinity, the outputs of this function are going to grow toward infinity that way. This is y, this is x. And also note that e to the power of 3x is equivalent to e to the x cubed. So if e to the x is growing toward infinity, then cubing it is just going to get there even faster, right? So for all those reasons, I know that this limit is going to grow toward positive infinity. In the denominator, same thing. If we think about the shape of the graph e to the x, x to the third power, it has this sort of a shape, goes this way, comes down this way. It has this sort of a shape, comes this way, comes across, and comes this way. Kind of roughly speaking, it goes that way, like that. Y, x. This is y equals to x cubed. So again, we see that if we choose values, as we choose values that go toward infinity, the output values are going to be growing toward infinity. So once again, I can conclude that this limit is infinity. So this is an indeterminate form of the type infinity over infinity. Okay, so we can use L'Hopital's rule. Let's rewrite it down here. So the limit as x approaches to positive infinity of e to the 3x divided by x to the third power is equal to, right, so we have this ratio here, is equal to the limit as x approaches to infinity of, and now we take derivatives, the derivative with respect to x of e to the 3x divided by the derivative with respect to x of x to the third power, right? And this is when we L'Hopitaled it. Right there. That's what allows that to happen. So now let's go ahead and take that derivative. This is the limit as x approaches to infinity of, and the derivative of the numerator is going to be equal to e to the 3x and then times a copy of 3 times using the chain rule. And then in the denominator, it'll be 3x squared. Well, this is still not going to be the answer I'm looking for. So I'm going to go ahead and try and evaluate this again. If I think about the limit as x approaches infinity of 3e to the 3x divided by the limit as x approaches to infinity of 3x squared, I'm still going to have infinity there and infinity there. So this is still an indeterminate form of type infinity over infinity. Indeterminate form of type infinity over infinity. Well, the good news is that you can use it again. We can apply L'Hopital's rule one more time to now this one. So now we say, okay, well, let's get the limit as x approaches to infinity of this 3e to the 3x divided by 3x squared. Well, let's L'Hopital it again. This is equal to the limit as x approaches to infinity of the derivative with respect to x of the numerator, which is 3e to the 3x, divided by the derivative with respect to x of the denominator, which is 3x squared. And we're going to say that this is allowed because L'Hopital. Okay, so this is equivalent to the limit as x approaches to infinity of, and well, this is just going to be equal to 9e to the 3x divided by 6x. And once again, we're going to get the same result. We're going to see that if we try and evaluate this, again, we're going to get that this is equivalent to the limit as x approaches to infinity of 9e to the 3x divided by the limit as x approaches to infinity of 6x. And once again, this is heading toward infinity, and this is heading toward infinity. Once again, we have that this is an indeterminate form of type infinity over infinity. So we get to use L'Hopital rule one more time. We get to use it as many times as we need to, as long as we continue to run into indeterminate forms that qualify, 0 over 0 or an infinity over infinity. So let's apply L'Hopital's rule one more time. So that means that the limit as x approaches to infinity of e to the 3x over, this guy, 9e to the 3x over 6x is equal to the limit as x approaches to infinity of the derivative with respect to x of 9e to the 3x divided by the derivative with respect to x of the denominator, which was that 6x, which is then equal to the limit as x approaches to infinity of, and then in the numerator we'll have 27e to the 3x divided by 6. Okay, so finally we get to something we can answer. This is equal to 27 over 6, just some number, times the limit as x approaches to infinity of e to the 3x. And as we've just established, this grows toward infinity. Oh, this looks kind of messy. Infinity. This is going to grow toward infinity, so the whole thing grows toward infinity. Okay, so let me zoom out and tie it all in. Okay, this is the original one we started with. We wanted to figure out this limit. We got to apply L'Hopital's rule once, and that led us to this answer. L'Hopital rule says if you want to find the limit of this fraction, that's okay. You can say it's equivalent to the limit of this fraction, right? We achieve it by getting derivative of the numerator and derivative of the denominator. Okay, but that didn't give us a valid answer. It still gave us an infinity over infinity. That's okay. We're going to use it again. So then I took that, kind of brought it over here, and then we applied L'Hopital's rule once again. And L'Hopital said, well, okay, if you're trying to find the limit of this ratio, L'Hopital it, and then that led us to this one, the limit of this ratio. Well, we tried to evaluate this, and we got the same deal. We got an infinity to infinity, still an indeterminate of type infinity over infinity. Type infinity over infinity. So we got to use L'Hopital's rule one more time. So, oops, I didn't write it. L'Hopital's rule. So we L'Hopitaled it one more time, and finally we struck gold. We were able to get to an actual answer. So that led us to this one. And this one, we can see, is heading toward infinity. So now we can tie it all back in and go back to our original limit, the limit as x approaches to infinity of e to the 3x divided by x to the third power then is, well, infinity, which remember is it's a fancy way of saying does not exist, right? We have a better idea of how it doesn't exist. It doesn't exist in the way that it goes toward positive infinity. Okay, so I hope I've given you enough to get started on your homework. Please come by my office hours if you have any questions.